This begins our study of circles. We're going to start with some basic terminology with regard to circles, some definitions. First off, a circle is a set of all coplanar points that are equidistant from a point which is called the center. If it didn't say coplanar, it said all points that are equidistant from a particular point in space, then that would be a sphere. So in the same plane makes it flat, makes it two-dimensional, or a circle. The symbol that we use to abbreviate to represent a circle is a circle with a dot in it. We don't just use a plain old circle because it looks like a zero. So if this is, we name a circle by the center. If this point is C, then we would name this circle Circle C, and that's how we'd write it. First term here, radius. You're familiar with radius. The radius is going to be the segment with endpoint at the center and on the circle. Radii is the plural in the United States. Radiuses is also correct, but try not to spray when you say that. Another term is the chord. A chord is a segment with both endpoints on the circle. So it would look like this. This is a chord. And of course, a diameter is also a chord. It has both endpoints on the circle, but it has the other special characteristic that it passes through the center. So a diameter is a special chord in that it passes through the center. A term that you've probably not heard is a secant. A secant is a line that intersects the circle in 2 points. That would look like this. A secant. A chord is a part of a secant. It's a segment within the secant. So this chord, for example, if you extended it, the lines, then that would be a secant. The secant is the portion of, the chord is the portion of the secant that's in and on side the, inside the circle and on the circle. We call it a secant segment in general, but this one with the endpoints in the circle is specifically a chord. Another term that you may not be familiar with in this context is the tangent. A tangent is a line that intersects the circle in exactly 1 point. That 1 point is called the point of tangency. You may have heard the phrase, somebody says, oh, don't go off on a tangent. Well, this is kind of what this is talking about. If you were like twirling something around and you were going to throw it, let go of it and let it go. You twirl it around, the centripetal force would keep it moving in the line that is the tangent. So if you were twirling something around like this and you let go of it, it would go this way. So the point then is, if you're saying don't go off on a tangent, that's like you let go of your real argument and you just went flying. And when you go flying, it's on the line of tangency. A definition of congruent circles. Congruent circles have the same radius. Let's look at a few examples here. Segment AE is a tangent. BH is tangent to both this circle and this circle. And this round thing here is circle C, because it's a circle and the center is C, so G, C. Circle G, we name it based on the name of its center. H is the point of tangency. Notice that the line BH is tangent to 2 circles. It's in common. So it's tangent to circle C at point B. It's tangent to circle G at point H. Segment DB is diameter. It's also a secant, it's also a chord, but it's a special chord. Line segment AB is a chord. Line AB is a secant. As we just saw there with two of the circles, one line can be tangent to two different circles. If it is, we call it a common tangent. It's common like, you like pizza? I like pizza. What do we have in common? We like pizza. Okay, so common. We have it in common. So here, these two circles have this line in common. It's tangent to this one, and it's tangent to this one. They both got it. It's common tangent. We call it an internal when it's between the circles, and external when it's not between the circles. So this is a common internal tangent. It's tangent to both circles, and it passes between the circles. This is a common external tangent. It's tangent to both circles, and it does not pass between them. Here's some examples. We talk about different types of tangents, common tangents. So the first one. Notice here that this has one common tangent. Right here. The point of tangency for both of them is the point where they intersect. This has one common tangent. These two do not have two common tangents. They are external. They'd have to be because you can't get between it. So there are the two common tangents for this circle. Notice if you try to draw another one in here, like this, that it passes both of the circles twice. It's not a tangent, it's a secant to both of them, so it doesn't count. On the snowman here, you have a common tangent between his head and his body, and that one's internal. You have two additional common tangents on either side of the snowman. So the snowman has three common tangents. Here are two separate circles. There are common tangents that are interior. They pass between the two circles. And there are common tangents. Oh, here's the other one. So two common internal tangents. And then on the outside, two common external tangents. So these two circles have a total of 4 common tangents. The circle in a circle has none. A definition here: concentric circles are circles that have the same center. In this case, there's lots of concentric circles, all that have the same center. Concentric, that's with the center. They're with the same center. They are concentric. Look at a few examples here. On the coordinate plane, A and C. A and C, do they have any common tangents? Let's see. They have external ones, one here on the axis, one up here. So those are common external tangents, and then the X between them. 4 common tangents. How about A and B? A and B have 2 externals and 1 internal. Notice if I ask you to write the equation of the common internal tangent, you count over this is at 6. So the equation of this internal tangent is, internal common tangent, is x equals 6. in your cipher, if you would, please draw a circle. Or this one, it's not as necessary that you draw it, but it'll help if you do. Okay, here's a circle, and I'm going to draw a tangent. So this line is tangent to the circle. There we'll take as the center of the circle. And now I want to draw the shortest distance from the center of the circle to the tangent. The shortest distance will be perpendicular. And look at the circle. What is it in the circle? In the circle, it is the radius. If you think about it, you'll see there's no other way to draw it. That the shortest distance between the center and the tangent is perpendicular, and it is a radius. Sounds like a theorem. So now get a compass and draw a circle. I'm going to use my mug here. It's my damn mug. She said, damn. Oh, no. Oh, well, let's look at it. I didn't say D-A-M-N. I said D-A-M. This is my Hoover Dam mug. So it's my dam mug. I got it, guess where? At Hoover Dam. I did. I thought of that when I bus driver. I was at the Star Trek Museum of the Future in Las Vegas, and I took a bus. Great museum. I took a bus out to Hoover Dam, and when I got on the bus driver said, "Ladies and gentlemen, I'll be your damn bus driver for today." And I said, "Oh my goodness!" And then I realized he was the bus driver taking us to the Hoover Dam, where I got this handy dandy little mug. Okay, so here's my mug. There's my circle I drew with my mug. You draw a circle even if you don't have a damn mug. Okay. Put a point out somewhere. Label it something really creative like P for point. Label it whatever you want. This is in your cipher, please, folks. Then draw the tangent, the line from the point tangent to the circle. So that means just barely touching at the point of tangency. Then draw the other tangent. You can draw two from every external point. Take your compass, set the point to point P, and set the pencil to your point of tangency as close as you can get it. Go ahead and mark it. Oops, mine's slipping around. I'm slipping around bad. I'm going to try that again. Okay. Put the point at the point of tangency. And that worked a little better. What you see is that the arc passes through both points of tangency. Remember that when you use a compass, the distance that it's set is the radius of the big circle that you're drawing with the compass. All radii are equal, so this distance to the first point of the top point of tangency is the same, is congruent to the distance to the bottom point of tangency. So we can mark them as congruent. These tangent segments from the external point to the point of tangency are congruent. Wonder if that just happened. Did it just happen? I don't know. I'm going to try one on the other side. Put one on the other side, either closer or farther away. I guess it can be point Q. And do the same thing. Draw your lines of tangency. From the external point to the points of tangency. Draw your tangents. Pick up your compass. See what happens. Set the point at point Q, the lead at the point of tangency. Oh my goodness, it worked. Again, the distance on the compass is the radius of the big circle that you draw with the compass. All radii are the same, so this tangent segment is the same as this tangent segment. Oh my goodness, lightning struck twice at the same time. Not really. It really is true. We've kind of demonstrated it. And it is the theorem. Tangents from the same point are congruent. Let's look at some applications of this and the other. So first off, is line segment AB a tangent? Well, if it were a tangent, it would have to be perpendicular. And it's not marked perpendicular. But wait, that's a 3, 4, 5 triangle, and methinks that's a Pythagorean triple, and therefore that is indeed a right angle, so AB is indeed a tangent, part of the tangent. How about this one? Looky there. I wonder if that one's tangent. It's not marked either. Well, you know what? We all had to memorize all of the Pythagorean triples with one digit less than 10. Was one of them 9, 15, 18? No, it was not. This is not a point. This is not a tangent. Let me show you what it looks like if you extend it. It really looks kind of like this, okay? If you do the Pythagorean theorem converse, you find out that this angle is not right. It is an obtuse angle. So it really should be drawn like this, where there's a little bit of gap there with regard to passing through. So this line is not a tangent, is in fact a secant. It passes the circle 2 times. Okay, if you'd like a little extra practice. Oh, wait, one more. One more. This one right here, number, right there. Here it is. Work this circle. Well, how are you going to find out what the radius is? Well, you're going to make yourself an equation. It's going to look like this. Pythagorean theorem. A squared plus B squared equals C squared. Notice that for C squared you must do the entire hypotenuse, R plus 16, parentheses R involved in the making of this. And proud graduates of Algebra 1, let's remember that that does not equal this. No. You have to do R plus 16 times R plus 16, which divided out becomes, multiplied out, expanded out, becomes this. You solve it down, and you find out that R equals 10. Go ahead and do a few of these if you'd like some practice. Here they are. I'll put the answers up, so pause it if you're going to work them. And here are the answers. This is useful in a number of circumstances. Here's one of them. This is an example of being out in space. Say you're an astronaut or you're on a satellite or something like that. Some of the things to remember when you're doing a practical example like this is that light travels in a straight line. So if you're asked how far can you see on the planet, the Earth is assumed to be a sphere here, even though it's not quite a sphere. So from B to A, the point at which you can stop seeing the Earth, that you can't see around the curve, the line of sight, the light that passes to your eye from there, forms a straight line, and it is tangent. It touches only at that point, right where the curve happens. Same deal down here. Both of these lines of sight are tangents, which means they're perpendicular to the radii. Here we have the circumference of the Earth given and the distance, and so various calculations can be done here with regard to this. To do that, you'd want to make a triangle with the radii and work around it and generally have a good time. Here's a challenge problem. See if you can give it a go. Go ahead and pause it. And just a hint, you're going to need to make some triangles inside this big triangle, maybe using some of the radii or something like that. See if you can figure out how long the radius is. Okay, pause it. And here's the answer worked out to help you with it. There's probably another way to do it, but the way I've chosen to do it is to make a triangle of half, split the triangle down the middle with the altitude. Then having done that, you notice I can get that. The reason I chose this is because I know this is 12 and this is 4. Why do I know this is 4? Oh, because I know it splits at half and 2 from our theorems regarding triangles, so I know that's 4 and 4. Okay, well then how do I know this is 8 and 4? How did I get that? Remember that tangent segments to an external point are congruent. Since this is 4, that's 4. Since the whole thing's 12, that must be 8. I work through the the red triangle, and I find out that the hypotenuse of the red triangle is 8 times the square root of 2. I take that and subtract the portion that's not in the blue triangle, purple, whatever that color is, and use that as the hypotenuse, work through it, and find the radius. And here endeth the lesson.